So this could be kind of a messy part here. So let me just jump into doing the second part of the practice test for Chapter 2. There's not that many problems. It ends at problem 17, so there's 4, 5, 6, 7 problems. Some of them have a couple parts, but most of them are pretty intense, but not problem 11. Problem 11 wants me to do the derivative of an e function, and that's the easiest kind of derivative. To do the derivative of an e function, you keep the e function exactly how it was given, and to the left of it you multiply by the derivative of whatever in the exponent. This exponent is x squared, and the derivative of x, to do the derivative of x squared, you bring the 2 in front of the x and you lower the exponent by 1. The derivative of x squared is 2x. That's what I'm going to write in front of my e function, and that's going to be my whole derivative. That's the whole answer for problem 11. I completely doubt that I have enough room to do number 12, so let me try to do number 12. In number 12, there's multiplication. 2y minus 4 is multiplied by e to the 5y squared. There's multiplication, and each piece has a letter, so that means I have to do the product rule. I need to take each piece that's being multiplied by the derivative of what it's being multiplied by. So I need to take the 2y minus 4 and multiply it by the derivative of e to the 5y squared, and I need to take e to the 5y squared and multiply it by the derivative of 2y minus 4. That's the product rule. I take each of the factors, 2y minus 4, which is one of the factors, times the derivative of the other factor, plus the other factor, e to the 5y squared, times the derivative of the opposite. Let me do these derivatives now. For the first piece, I'm just going to bring down the 2y minus 4. And for the second piece, I'm going to do the derivative of an e. Super easy to do the derivative of any e. I just write that e function down, and right to the left of it, I take the derivative of whatever in its exponent. The derivative of 5y squared is 10y. So right to the left of that e to the 5y squared, I'm going to sneak a 10y. I'm going to bring my plus sign down, and I'm going to move on to the next piece. The next piece, I carry down the e to the 5y squared, and after it, I put the derivative of 2y minus 4. The derivative of 2y is 2 because the derivative of any first power term is its coefficient. The derivative of 4, because it doesn't have a letter, is 0. That's technically the derivative. Let me clean this up a little bit by doing a few multiplications. I'm going to take this 2y and multiply it by the 10y e to the 5y squared. And I'm going to take the minus 4 and multiply it by that 10y e to the 5y squared to clear that parentheses. And when I clear that parentheses, I'm going to do this multiplication and get 20, which is 2 times 10, y squared, which is the y times y, e to the 5y squared. The next multiplication, I'm going to multiply the negative 4 and 10 and get negative 40 y e to the 5y squared. And the last piece, the e to the 5y squared times 2, I'm going to leave this plus sign and write plus 2 e to the 5y squared. So I cleared that parentheses, and now I'm going to clean this up by pulling out a common factor. If I look at the numbers that don't have letters, 20, 40, and 2, all of those numbers are divisible by 2. Part of my common factor is going to be the number 2. When I look at the letters, there's a y squared, a y, but there isn't a y there. I can't pull out a common factor of a letter with a y. So I'm going to leave the y's alone. But I'm not done with my common factor because all 3 pieces have an e to the 5y squared. I'm also going to factor out that e to the 5y squared. So there's my common factor. And I'm going to figure out what's left in the parentheses by just taking away what I need to take away. The first piece had a 20. I factored out a 2, so I divide that 20 divided by 2, and I get 10. The first piece had a y squared. I didn't factor out any single letter y, so that y squared is going to stay. The first piece had an e to the 5y squared. I factored it out, so now it's going to be gone. I'm going to bring down the minus sign. Middle piece had a 40. I factored out a 2. I'm going to divide that 40 by 2 and leave a 20. It had a y. I didn't factor out a y, so I'm going to leave that y. I factored out the e to the 5y squared, so I'm not going to write that. I'm going to bring down this plus sign. The second piece, I started with a 2. I factored out the 2. I'm going to divide that 2 by 2 and be left with a 1. And I factored out the e to the 5y squared. I've pulled out my common factor. I don't think that factors, and even if it did factor, I'm not going to make a go at factoring it. That's going to be my answer to number 12. I also don't think I can do that nicely on one sheet of paper, so let me do 13 on a separate sheet of paper. I need to use the quotient rule because there's dividing. There's no plus or minus in the denominator, so maybe I can rewrite it to avoid the quotient rule, but that e makes it really kind of hard to do. So let me just live with the problem and see what I can do. So I'm going to take the derivative using the quotient rule. The quotient rule says take the denominator, multiply it by the derivative of the numerator, which is going to be the derivative of 5t to the 4th, then minus the numerator times the derivative of the denominator all over the denominator squared. So that's the template for my derivative. And let me do the few derivatives, and I'm going to do something different with the denominator. So first thing I'm going to do is start working on this numerator. The first piece, I'm going to leave the e to the 2t. I'm going to leave this times sign, and after it I'm going to put the derivative of 5t to the 4th. I'm going to go 4 times 5 is 20. I'm going to lower the exponent from t to the 4th to t cubed. I'm going to bring this minus sign down. I'm going to leave this 5t to the 4th. And then I'm going to do the derivative of e to the 2t by writing that e to the 2t down, leaving myself some room, and to the left of that e to the 2t, write the derivative of its exponent. Its exponent is a first power term, so the derivative is the number in front of the letter, which is 2. That exponent has a derivative of 2. And in the denominator, instead of writing e to the 2t squared, I'm going to write e to the 2t times e to the 2t. Squaring something means to multiply it by itself, and it's going to be easier when I cancel if I don't have the square and I have the e to the 2t written twice. Let me write this a little bit better before I get into canceling. Specifically, this looks weird to me having the e second, so I'm going to write the e first. Second. It looks weird having the e first. I'm going to write the e second. And in this middle piece, I'm going to multiply the 5 and the 2. And get minus 10t to the 4th times e to the 2t. And I'm going to leave the denominator alone for a second. Now I'm going to start working on that numerator, and I'm going to get my common factor. First I'll work on the numbers. Between this 20 and that 10, the biggest number that divides evenly into those is going to be a 10. So in front of a parentheses in the numerator, I'm going to write a 10. The next thing I'm going to worry about are the t's. There's a t cubed and a t to the 4th. I take the smaller of the exponents when I go for my common factor, which is going to be a t cubed. And they both have an e to the 2t. I'm going to factor out and also an e to the 2t. That's going to be my common factor in the numerator. And now I have to figure out what's left after I pull out that common factor. The first piece had a 20. I factored out a 10. I'm going to divide that 20 by 10 and be left with a 2. The first piece had a t cubed. I factored out a t cubed, so it's gone. The first piece had an e to the 2t. I factored out an e to the 2t, so it's gone. Second piece had a minus 10. I factored out a 10. I'm going to be left with the minus. Technically, I'm going to be left with a 1 if I divide that 10 by 10. I don't need to really write that 1 if there's going to be something else left afterwards, and there is going to be. The second piece had 4 t's. I factored out 3 t's. It's going to be left with 1 t. Second piece had an e to the 2t, and I factored it out. So what's left inside the parentheses is just 2 minus t when I factor out that common factor. Now I can cancel the common factor of e to the 2t with one of the e to the 2t's in the denominator, and I'm about to write something that I'm going to call my answer, even though the parentheses might bother you that the t is written second and it has a negative in front of it. I'm going to go ahead and call this my answer. If you went further and worked on that parentheses, wrote the t first and the 2 second, and factored out a -1, it'd be absolutely okay and really nice. I'm not even going to explain how to get this, but for those of you that went the extra step, if you wrote this down for your answer, that's ultra impressive. That would involve writing the t first and the 2 second, making this -t plus 2, factoring out a negative, put it in front of the t squared, and flipping the signs. I didn't explain that, but if you just instinctively did that, that's beautiful, but I'd expect you to stop right there unless you just, want it to go further. 14's a friendly problem. To do the derivative of an ln, you just form a fraction. In the denominator of the fraction, you write whatever the argument of the natural log is. In this case, it's 3t to the 5th. So ln's are super easy derivatives, just like e are easy derivatives. So ln's, the derivatives are fractions. The numerator has the denominator has the argument. The numerator is going to be the derivative of this denominator. So up above the numerator, in the numerator, I'm going to take the derivative of 3t to the 5th by multiplying the 5 times 3 and getting 15, and lowering the exponent by 1. That's an unsimplified form of the derivative, and the 15 over 3 is easy for me to simplify. That just reduces to 5. The t to the 4th over t to the 5th is also easy for me to simplify, but it might not be as easy for you. So I'm going to write 5 in the numerator because the 15 over 3 reduces to 5. And then for the t to the 4th over t to the 5th, the numerator has 4 t's, the denominator has 5 t's. I could cancel all 4 t's from the numerator with 4 of the 5 t's from the denominator, and I'd be left with 1 t in the denominator. The derivative of problem 14 is just 5 over t. This is wearing me out. 15 is a multiplication problem. It's multiplying x squared times ln of x. It's a multiplication, and both factors have an x. When you're doing a derivative with multiplication, if both factors have a letter, you have to use the product rule. So in 15, I'm going to say y prime, and I'm going to do the product rule. It's going to be x squared times the derivative of ln of x plus ln of x times the derivative of x squared. The two pieces that are being multiplied get multiplied by the derivative of the opposite piece. I'm going to clean this up real quickly by finding my derivatives. The first derivative I need to take is the ln of x, and the derivative of an ln doesn't have an ln in it. I take the argument x and put it in the denominator, and then I take the derivative of that and put it in the numerator. The derivative of an x without an exponent is just the number in front of the x, and there's an implied 1 in front of the x. So that's going to be 1 over x for the derivative of ln of x. The second piece is the ln of x times the derivative of x squared. The derivative of x squared is just 2x to the first power. The only thing I'm going to do to clean this up is cancel one of these x's. Technically, this x squared is x times x, and then it's times 1 over x. I can cancel one of the x's from the x squared with the x in the denominator, cancel out the fraction, and leave myself with x times 1, which is just x. So this first simplifying, the fraction cancels, one of the x's cancels from the denominator, I'm left with 1x in the numerator. Technically, after I do that, fraction is gone, I'm left with 1x there times a 1, which is x. And then the second piece, I can't multiply these together. To me, it looks odd seeing the ln of x written first. This is an absolutely perfect answer for problem 15. If you want to, you can pull out a common factor of an x. If you pull out a common factor of an x, that x, because I pulled it out entirely, I need to leave a 1 behind. And the second piece, if you pull the x out, you'll be left with both the 2 and the ln of x. both of these are perfectly fine answers. Again, I'm not going to ding you too much for missing common factors. Anything that I boxed on this test is going to be considered okay. 2 more problems. So, another find the values where the tangent line is horizontal. We had one of those on the last review. So let me just jump into this. This means to find out where the derivative is equal to 0. So I'm going to find the derivative. This is an e function. To find the derivative of an e function, I write the e function down. I'll leave some room to the left of it. To the left of it, I simply take the derivative of the exponent, and the derivative of x squared is 2x. Once I find the derivative, if I'm asked to find where tangent lines are horizontal, I take the derivative and set it equal to 0. This derivative is factored, so I need to take each of the factors and set them separately equal to 0. So I'm going to take the 2x and set it equal to 0, and the e to the x squared and set it equal to 0. When I set the 2x equal to 0, I divide both sides by 2 and get x equal to 0. And for the e to the x squared equal to 0, there's no solution. So the value of x that I need, the answer to part A is just going to be x equal to 0. Part B wants me to find an equation of a tangent line at this value of x. To find an equation of a tangent line, I need both a point and a slope. The algebra that I did, or the calculus that I did, gives me the x-coordinate of the point. The fact that I'm finding where tangent lines are horizontal sneakily gives me the slope, because horizontal lines all have a slope of 0. What I don't have is the y-coordinate of the point, and I get the y-coordinate of the point by plugging in 0 for x into the original function. And plugging in 0 for x would give me e to the 0 squared. 0 squared is 0, that would give me e to the 0, and anything to the 0 power is 1. So the y-coordinate of the point I'm looking for is 1. And now I'm going to use the formula y minus y1 equals m times x minus x1. And I'm going to go y minus, in for the y1 I'm going to plug 1, equals m, I'm going to plug in 0. And in for x1 I'm going to plug 0. So I'm going to get y minus 1 equals 0 times x minus 0. I'm going to leave the right side y minus 1, left side y minus 1. On the right side, I'm going to clear the parentheses. I'm going to go 0 times x is 0. 0 times minus 0 is 0. When I clear the parentheses, the right-hand side comes out to be 0. I'm going to solve this for y by adding 1 to both sides. And that's going to be the answer to part B. One more problem, and it looks pretty imposing, but it really isn't, but it's a word problem. And this word problem gives me an equation. It's a cost function. It says that the cost for making x supersized candy bars is given by this formula. C equals 2 ln of x plus 0.15. Part A says find the derivative of this. Pretty easy to find the derivative of this because it's not so bad of a derivative. The first thing I need to realize, I need to take the derivative of each piece. I need to take the derivative of 2 ln of x. I need to take the derivative of plus 15, plus 0.15. The derivative of the plus 0.15 is 0 because it doesn't have an x, so I don't really have to worry about that. Ultimately, I just need to take the derivative of 2 times the natural log of x. There's multiplication here, so it feels like I might need to use the product rule. 2 is being multiplied by ln of x. Because both of the pieces don't have an x, I really don't have to do the product rule. I just need to leave the 2 out front and multiply it by the derivative of the natural log of x. And that's how I'm going to find the derivative. I'm going to multiply 2 times the derivative of the natural log of x. To do the derivative of the natural log of x, I form a fraction. In the denominator, I put the argument, which is x. And in the numerator of that fraction, I take the derivative of what I just put in the denominator. Because the denominator has an x to the first power term, the derivative is the number in front of the x, and there's an implied 1 there. I'm going to multiply this out. I'm going to multiply the 2 by the 1, and I'm going to say my answer to 17a is just 2 over x. Now I have 2 bits of interpreting and evaluating. Part B says take 4 and plug it into the original function, not into the derivative. And I'm just going to do that on my calculator. I'm going to round to 2 decimals, assuming I'm going to need to round to 2 decimals. This function gives me the cost of making candy bars. X is 4. It's going to give me the cost of making 4 candy bars. What I'm doing right now is I'm going to get a number. And since I plugged it into the original function, and the original function tells me how much it costs to make supersized candy bars, I'm going to interpret my number here in a second. So numerically, I'm going to round to 2 decimals. And this is a cost function, so this is giving me a cost. And if I want to interpret my answer, it's going to say it's going to cost a total of $2.92 for this company to make 4 of these supersized candy bars. So I'll say $2.92 is the cost to make 4 of these candy bars. So does that make them like about 75 cents a piece or so? Part C wants me to plug a value 4 into the derivative. The derivative is the marginal cost function. When I plug a value into the derivative, it doesn't tell me the total cost, it tells me the cost of making the next candy bar. So let me do C prime of 4 real quickly. To do C prime of 4, I'm going to plug 4 into this function for x. That's going to be 2 over 4. And I know that 2 over 4 is 0.5 or 0.50. So I get C of 4 is 0.5, which is a half a dollar or 50 cents. If I want to write this as a dollar, I'm going to say dollar sign 0.5, maybe 0.50. And that's what I get when I plug 4 in, round it to 2 decimals. I'm putting a dollar sign because these functions are giving me dollar amounts. And the dollar amount that this is going to tell me, it doesn't tell me the total cost of making 4 candy bars. It tells me is the cost, this is the cost of making the next candy bar, which is the 5th candy bar. So the derivative of a cost function can be used to get a marginal cost, and marginal cost is the cost of the next item. In this case, because we're making candy bars, it's the cost of making a candy bar, and the next item, since I'm talking 1 more than 4, would be the 5th candy bar. So that's absolutely everything that's on the Chapter 2 test. It's a monster test, really, because all these derivative rules can really get confusing. So, spend some time with this. Come visit me in my office, and I'll sit with you and help you understand the derivative rules if you don't have them perfected.